The art of forecasting stock prices has been a difficult task for many of the researchers and analysts. In fact, investors are highly interested in the research of area of stock price prediction. For a good and successful investment, many investors are keen on knowing the future situation of the stock market. In such a scenario, an effective prediction system for stock markets help traders, investors, and analysts by providing supportive information like the future value of certain stocks. Hi all, I welcome you to this stock prediction session using machine learning. In this work, I present a recurrent neural network and long short-term memory or LSTM approach to predict stock market indices. So without much ado, let's get started. So on our agenda today, I'm going to start out by a little introduction on this piece. Then I'm going to explain to you what an LSTM is, and then we're going to move on straight to our model before concluding this session. Also, don't forget to subscribe to us and hit that bell icon to never miss an update from the Edureka YouTube channel. And if you want to know more on machine learning, data science, or any other related field, do not forget to check out our certification trainings, the link to which I will leave in the description box below. So let's get straight to the introduction, shall we? Now, there's a lot of complicated financial indicators, and also the fluctuation of the stock market is very, very violent. However, as the technology is getting advanced, the opportunity to gain a steady fortune from the stock market is increased, and it also helps experts to find out the most informative indicators to make a better prediction. For those of you who do not understand stocks are basically an equity investment that represents part ownership in a corporation or a company. It entitles you to a part of that company's earnings and assets. Now, the prediction of the market value is of great importance to help you in maximizing the profit of your stock option purchase while keeping the risk low. And this is important because you need to invest your money in a stock which is going to increase in value over time and not decrease. So RNNs, or recurrent neural networks, have proven to be one of the most powerful models for processing sequential data. The long short-term memory is one of the most successful RNN architectures. Now, the LSTM introduces the memory cell, a unit of computation that replaces the traditional artificial neurons in the hidden layer of the network. With these memory cells, networks are able to effectively associate memories and input remote in time. Hence, they suit to grasp the structure of the data dynamically over time with high prediction capacity. Now, this is what the LSTM architecture looks like. We have the forget gate. Now, for the sake of the illustration, let's assume that we are reading words in a piece of text and want to use LSTM to keep track of grammatical structures, such as whether the subject is singular or plural. If the subject changes from singular word to a plural word, we need to find a way to get rid of our previously stored memory value of the singular or plural state. In an LSTM, the forget state lets us do this. Here, WF are weights that govern the forget gate's behavior. We concatenate the value in the square brackets and multiply with the weight. The equation results in a vector called tau f with values between 0 and 1. This forget gate vector will be multiplied element-wise by the previous cell state. So if one of the values of tau f is 0 or close to 0, then it means that the LSTM should remove that piece of information in the corresponding component. If one of the values is 1, then it will keep the information. Next, kindly pay attention to the update gate. Once we forget that the subject being discussed is singular, we need to find a way to update it to reflect that the new subject is plural now. There is a set formula to update the gate. Similar to the forget gate, here tau u is again a vector of values between 0 and 1, and this will be multiplied element-wise with CT in order to compute the value. To update the new subject, we need to create a new vector of numbers that we can add to our previous cell state, which gives us our final new state. And finally, I have to discuss the output gate. Now, to decide which outputs we are going to use, we will be using two formulae which are given on your screens right now. The first equation is where you decide what to output using a sigmoid function. And the second equation, you multiply that by the tan h of the previous state. Now, I wouldn't go much into it, but let me just conclude this section by saying that LSTMs are basically explicitly designed to avoid long-term dependency problems. Remembering information for longer periods of time is practically their default behavior. It is not something they struggle to learn, unlike the more rudimentary model of an RNN. So let's get straight into the model. Now, the model I'll be using today is based on Google Stock Prediction. Now, this is an RNN model that I saw a couple of places floating around. So I'm not sure who originally did it, but it's a great way to start understanding how you can use RNN and LSTM to do stock prediction. Okay? So how this is going to go is I'm going to discuss the methodology for a little bit, and then I'm going to run it on Jupyter Notebook and show it to you. Yes? All right. So we'll go through this step by step. First step is the raw data, obviously. In this stage, the historical stock data is collected from the Google stock price, and this historical data is used for the prediction of the future stock prices. I hope this much is clear. Now, don't worry, the dataset that I will be using, the training, the testing data, as well as the code that you'll be seeing right now, I'll leave the links to all of these things in the description box below. So you can follow along if you like, or also run them later to see if you can. So this is the model again. The first thing we're going to do is import the libraries. So I'll take a little bit of time discussing all the libraries. We are using NumPy so that we can apply mathematical functions and operations to our arrays, multidimensional arrays. Then we are using matplotlib for visualization purposes. We are using pandas, which is basically a data analysis and manipulation tool. And what's cool about pandas is that it takes data like a CSV file or an Excel file or an SQL database and creates a Python object with rows and columns called a data frame, which looks very similar to a table in a statistical software. Yes. And then finally, we are also going to be importing datetime library to work with dates as date objects. So quickly going to run that. Next, what I'm going to do is read the dataset as our step mentioned. Here's the raw dataset. And I'm also going to go ahead and display the head. The head meaning the top 5 rows present in my dataset. As you can see, we have open, high, low, close, and volume along with date, which are the 6 columns present in any stock history type of a dataset if you go through them. Now, the listed close or the listed closing price is the last price that anybody paid for a share of that stock during the business hours of the exchange where the stock trades, or the open is the price from the first transaction of a business day. Apart from that, there's also high and low. High basically means the highest price in a given period of time, and low means the lowest price in a given period of time. And finally, you might see the last column, which is volume. It's nothing but the number of shares or contracts traded in a security. In context of a single stock trading on a stock exchange, the volume is commonly reported as the number of shares that changed hands during a given day. The transactions are then measured in stocks, bonds, options, contracts, future contracts, and commodities. All right. Now, since I have used head here, you can see the top 5 rows. If I would have used tail and run it, here you can see the bottom 5. So now you can see our data starts from the 3rd of March 2012 and goes up to the end of December 2016. Okay, so next what I'm going to do is I'm going to check if any of my data is not applicable. This right here, this is any function right here, is used to detect missing values. It returns a Boolean same size object indicating if the values are not applicable. Now, not applicable values such as none or numpy nan gets mapped to true values and everything else gets mapped to false values. Now you can see all of our columns here show false, which basically means we have no non-applicable values. Then we are printing out the basic info of our datasets. That's what this function does. We can see all our 5 columns, all their non-none values, their data types, along with memory usage. Finally, we are printing out the growth of the price in stocks from 2012 to 2017. It goes up like this. As you can see, it has risen quite a lot over 5 years. And why wouldn't it be? We are talking about Google. And if I'm not wrong, Google's parent company saw its stock price rise by almost 85% between 2014 to 2017, going from about $820 to $1,519 in 3 years. The rise was primarily driven by a significant increase in total revenue and a slight decrease in the shares outstanding. Now I'd like you to go back and check the data type. As you can see, 3 of the columns have float as the data type, while 2 have object. So to homogenize it, what we're going to do is we are going to convert the column types of the data frame. All right. Now the next thing we're interested in is what is the 7 days rolling mean of our stock price. This means, in the simple example, that for every single stock prediction, we look 7 days back, collect all the transactions that fall in this range, and get the average of our column. Luckily, this is extremely easy to achieve with pandas. So here we go. As you can see, the first 6 days do not have any output. It is going to start from the 7th day as we have taken the rolling mean of 7 days. All right. And as I had mentioned earlier, the head function here is going to give us the first 20 rows. Here we are basically taking a bracket of 7 days and we're getting the mean of the previous 7 days iterated every day forward after the 7th day. Yes? And this is how it compares with the previous graph that we had gotten. We had the rolling means in orange and we have our previous graph in the same blue. This right here basically gives you the moving average of the past 30 days. Let's now try and plot the close column versus the 7-day moving average of the close column. So when we look at this plot, the blue line here is the close price column and the orange line here is the 30-day rolling mean of the close price column. Now you also have an option of going ahead and specifying a minimum number of periods for this. So if you just keep like the minimum period of 1, this is what your graph is going to look. Here we are basically trying to say that the minimum number of observation per window, which is of 30 days, should be 1. And this is why our graph looks like this. And with that, we are creating our first data frame, which is of the training set. And that's it. And reading the contents of the data set using pandas. Now, what do we do when we take into account everything from the start of this time series to the rolling point of the value? Now we're going to be data pre-processing. We are at our stage 2. The pre-processing stage involves data discretization, where we'll reduce a part of our data but with particular importance for the numerical data. Next, we are going to do a data transformation, which is basically nothing but data normalization. Then we're going to clean the data, fill in the missing values. We're going to integrate our data files. And after the data set is transformed into a clean data set, the data set will be divided into training and testing sets so as to evaluate. So in the end, what we are trying to do here is creating a data structure with 60 timestamps and 1 output in total. So we're going to start out by cleaning our data. We are doing the same thing which we had done before, is checking if there's any not applicable possibilities, and then move on to feature scaling, for which we are going to be importing min-max scaler from scikit-learn, which is nothing but a machine learning library for Python. We'll be using the min-max scaler to transform features by scaling each of them to said range. And here our feature range is 0 to 1 for obvious reasons. Then we're going to go ahead and run it. Then finally, we are going to be creating a data structure with 60 timestamps and 1 output. So basically what we're trying to do here is that we're basically going to take the data from day 1 to day 60 and then make predictions on the 61st day. And then we are going to follow it up by taking data from day number 2 to day number 61 and then predict on the 62nd day. So our I is going to go from 60 to the end of our range, which is 1258. And then we are going to append it to the X train and Y train. X train starts at I minus 60. So if I is 61, then I minus 60 is 1. It starts from I minus 60, so it starts from the first day, ends at 61. And then the Y train is basically going to give us our prediction on the ith day, which if we take 61 is our first prediction from the first 60 days. So Y train is going to give us the prediction on the 61st day. So we're going to be appending both of these trains and then reshape the data. Next is stage 3, which is for feature extraction. Now in this layer, what we're going to do is we are going to choose only the features which are to be fed to the neural network. We'll be choosing features from date, high, low, close, and volume. So to start off with that, we're going to start by importing Keras libraries and packages. This is going to be the first step towards building your RNN. Keras is basically Tensorflow's high-level API for building and training deep learning models. And here we're going to import 4 libraries. First is sequential, which is basically a linear stack of layers through which you can create a sequential model by passing a list through it. Then we are going to input something known as dense. Now the dense layer is the regular deeply connected neural network layer. It's the most commonly and frequently used layer, and it's used to change the dimensions of your output vector. The dense layer basically represents a matrix vector multiplication. So the values in the matrices, which are trainable parameters, get updated during backpropagation. So if you get an m-dimensional vector as an output, a dense layer is used to change the dimensions of your vector. Next, we are going to be initializing our RNN. So for a time series problem like this, we are basically going to be using a regression model. So for our regression deep learning model, the first step is to read in the data, which is a sequential data, and we are going to assign this to the model called regressor. With that, we are moving on to stage 4, which is the most important stage here, and that is training the neural network. In this stage, your data is going to be fed to the neural network and trained for prediction. You're going to assign random biases and weights to your model. Now, this LSTM model is composed of a sequential input layer followed by 3 LSTM layers and a dense layer with activation, and then finally a dense output layer with the linear activation function. So here you can see the first input layer. You have your units, return sequences, the input shape, and then the dropout. Now, dropout basically is a regularization technique for reducing overfitting in neural networks. So it drops out units in a neural network. Then you have your 3 layers. Yes. And then finally you have your output layer. And since you need only one output, units equals 1. Next, what you're going to do is compile your RNN. Here you're going to be using something known as an optimizer. And let me just begin by saying that an optimizer is one of the 2 arguments that are required for compiling from the Keras model. Now, the type of optimizer used can greatly affect how fast the algorithm converges to the minimum value. Also, it is important that there is some notion of randomness to avoid getting stuck in a local minimum and not reaching the global minimum. Now, there are a few great algorithms, but I have chosen to use the ADAM optimizer, which combines the perks of the ADA-GRAD and the RMS prop optimizers. Now, the ADA grad optimizer essentially uses a different learning rate for every parameter and every step. The reasoning behind it is that the parameters that are infrequent must have larger learning rates, while parameters that are frequent must have smaller learning rates. Makes sense, right? In other words, the learning rate is calculated based on the past gradients that have been computed for each parameter. Now, the RMS prop considers fixing the diminishing learning rate by only using a certain number of previous gradients. Now that we understand how both of these optimizers work, we can look at how ADAM works. Now, the adaptive moment estimation, or ADAM, is another method that computes the adaptive learning rates for each parameter by considering exponentially decaying average of the past squared gradients and the exponentially decaying average of past gradients. Now, what you see on the screen are how they are represented. The V and the M can be considered as the estimates of the first and second moment of the gradients respectively, hence getting the name adaptive moment estimation. When this was first used, researchers observed that there was an inherent bias towards zero, and they countered this by using the two estimates you see on your right, which leads us to our final gradient update rule. This is the optimizer that I'm using, and the benefits are quite a bit. Now, because of this, the learning rate is different for every parameter and every iteration and does not diminish as with the ADA grad. The gradient update uses moments of the distribution of weights, allowing for a more statistically sound descent. Now, another important aspect of training the model is making sure the weights do not get too large and start focusing on one data point, hence overfitting. So we should always include a penalty for larger weights, where of course the definition of large would be depending upon the type of regularizer used. And I have chosen to use the Tikhonov regularization, which can be thought of as a minimization problem. The fact that the function space is in the reproducing kernel Hilbert space ensures that the notion of a norm exists. This allows us to encode the notion of the norm into our regularizer. And finally, we're going to talk a little bit about dropouts. Now, a new method of preventing overfitting considers what happens when some of the neurons are suddenly not working. This forces the model not to be overdependent on any groups of neurons and consider all of them. Dropouts have found their use in making the neurons more robust and hence allowing them to predict the trend without focusing on any one neuron. Here is the result of classification error percentages with and without the dropout. As you can see, without the dropout, they are way higher than with the dropout. So upon running, fitting the RNN into a training set, we have our epochs equals 100 and batch size equals 32. Epoch is nothing but a frame of time in machine learning. It indicates the number of passes through the entire training dataset the machine learning algorithm has completed. And here we also have something known as a batch size, which refers to the number of training examples utilized in a single iteration. Usually, this is the number that can be divided into the total dataset size. And in general, 32 is a good starting point for a batch size. You could also go with 64, 128. You get it, the multiples of 32. But 32 is a good range to start experimenting with. Let's put it that way. So in this layer, you can see the output value has been generated by the output layer of the RNN and is compared with the target value. The error or the difference between the target and the obtained output value is minimized by using backpropagation algorithm, which adjusts the weights and the biases of the network. We followed the same for test data pre-processing. Finally, we are going to be making the predictions and visualizing the results. We are getting the real stock price of 2017, for which we are doing exactly what we did for the data pre-processing part. Here we are using ILOC or ELOC, depends on what you guys call it, to select rows and columns by number in order that they appear in the data frame. You can imagine that each row has a row number from 0 to the total number of rows, and ILOC allows selections based on these numbers. So now basically we have a prediction. The head of the data or the first 5 rows are from the 3rd to 9th of January of 2017. We are again doing the same thing that we did previously. We are checking out the dataset info. We have all the columns. We have the date time index of all the entries. We have the memory usage. We also have the data types. Here again, volume comes up as object instead of float. So we are again replacing it with float. Here again, reading the test set and putting it in a data frame and getting out the info. And finally, to get the predicted stock price out of 2017, we're going to merge the training set and the test set on the 0th axis. As you can see right here, we're going to set the time step as 60 as we had done previously and reshape the data. Our X-test list we are going to be assigning to predicted stock price and then taking an inverse transform of it to get it out of the matrices form. Here you can see the information on the predicted stock price data frame. And finally, we're going to use matplotlib to visualize the result of the predicted stock and the real stock price. From the plot, you can see that the real stock price went up while our model also predicted that the price of the stock will go up. This clearly shows how powerful LSTMs are for analyzing the time series and the sequential data. All of the analysis here has been implemented with relative ease thanks to Keras and the functional API. Now, in conclusion, I'd like to say that the popularity of stock market trading is growing extremely rapidly, which is encouraging researchers to find out new methods for the prediction using new techniques. The forecasting technique is not only helpful to researchers, but also helps investors or any person dealing with the stock market. In order to help predict the stock indices, a forecasting model with a good accuracy is required. In this work, we have used one of the most precise forecasting technologies using RNNs and LSTM units, which help investors, analysts, or any person interested in investing in the stock market by providing them a good knowledge of the future situation of the stock market. In such little time, at least we were able to get the trend right? So that's it for today, guys. I'll be really happy to hear any questions or feedback in the comment section below. I'd leave you with that thought. My name is Upasna. Thank you and have a great day.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!